All right, so I said you could do this using a loop invariant, but we're going to do this by sort of building an intuition using some pictures here. So how many different types of paths do we consider each iteration? So we have some start vertex, and in the current iteration, we're basically saying that we have another vertex that's not been found, and we're going to compute the shortest path to that one. Or rather, the shortest path we compute to it is the shortest path, and there's no other shorter path. Well, we can have a bunch of other vertices here, so we can have S pointing to other vertices, and those vertices pointing elsewhere. We can have some other vertexes that haven't been found yet, vertices that haven't been found yet. So this is sort of the more general picture. But there are some that we can care about a little bit more. So for example, we can have V star, and V star is just the vertex that's connected to S already. The squiggly line here is just to denote that, you know, it's not, doesn't have to be directly connected. There could be any number of vertices on that path. And V star is the vertex that is the next in the path to get to Vmin along the shortest path. So the one that we just computed with Dijkstra's greedy criterion. But how do we know that that's better than some other path to Vmin? So we could have another squiggly path of however many vertices to get to X. How do we know that's not a shorter way to get to Vmin? And then how do we know if there's not some other vertex we haven't found yet, Y, that through some other path has an even shorter way to get to Vmin? So we're going to directly compare all these vertices. That's all possible cases we have. We could have that to get to Vmin, we have our shortest path, or we could have another found vertex that gets to it, or there could be another unyet found vertex that has a shorter path to it. There's no other way to get to Vmin to find a shorter path later on than what I've got pictured here. So each of these vertices, each of these edges that cross this boundary, this dashed line boundary from the found set to the not found set, has some weight associated with it. And there's some positive edge weight, or I guess I should really say non-negative. Non-negative edge path length from S to V star and from S to X. How do we know they're non-negative? Well, the length of all those edges has to be 0 or greater. So there's no way to have a negative path length. Dijkstra's algorithm tells us that this is the shortest path to get to Vmin, and there's no shorter path that could ever be found. So let's take a look at the different cases here to compare. Let's start by comparing these two. So how do we know that the path from V star to min is better than the path from V star to Y? So that one's actually very easy to look at because both include the path from S to V star. So for example, the path length to get from V star to V min is equal to whatever the path length is to get from V star to, from S to V star. Plus this weight going from V star to V min. So that's the total path length that we computed to get to V min. And what about getting to this other vertex Y? Well, this is the same path length. So they both go through V star. So basically what we're doing is we're directly comparing these two edges. So those are the same. We're basically directly comparing this edge, and Dijkstra's will, in code, directly tell us which of those is the smaller value. So inside that innermost nested loop, so if I jump back to the code, we're always taking the smaller edge, the smaller path, which in this case is the top one because this edge is smaller than this one. That's the only way we would have marked this one as Vmin. Okay, so we directly compared those two. How do we know that the path to V star to Vmin is not shorter than some path V star down to Y up here to Vmin? Well, again, we know that this is some non-negative, I should really change that, some non-negative path length. We know that because that's the only type of graphs we operate on with Dijkstra's. Which means that if we come down here to Y, we can only end up adding to the path length, which would not minimize the path length. So Dijkstra's algorithm only operates with graphs with positive edge weights. Thus, the new path has to be greater than or equal to. It could be that all the vertices on this path, the edges on that path, are 0, and we still wouldn't have gained anything. So it's not that there's a unique shortest path to Vmin, but this is one of them, and there's no reason to go through a different one. All right, well, how about this? Why do we know that the path from V star to Vmin is better than the path from X going through X to Vmin? Well, again, we directly compute these, or compare these. In Dijkstra's algorithm, we would say each of those vertices, so x and v star, would be counted here as v, and we would directly compare what we compute here in the if statement. So Dijkstra directly compares these two paths, and it found that this one going across the top was cheaper. And again, how about comparing the top one to this bottom one? Well, we know that it was cheaper to go from v star to v min than it was x to v min. And we also know that going from v star to v min is cheaper than x to y, otherwise y would have been v min. So that means that going from x to y is greater than going from v star to v min. And then again, all we're doing is adding even more, potentially, to that path length here. Okay, so we've considered all possibilities here. Let me give you some concrete examples, or some concrete things to remember. It's not that we always take the shortest edge. We're always considering the shortest path. So, for example, let's say the path length from s to v star is 10. The path length from s to x is 20. It could be 14 to get from v star to v min, and 5 to get from x to y, 15 to get from v star to y, and 8 to get from x to y. I think I called this one x to y, but that one's x to v min. All right, well, what's the shortest weight? The shortest weight is this one. But when you take into account path lengths, it's not the shortest path length. This is the shortest total path, which means we're going to take this cost of 14, even though it's not the shortest weight, crossing that gap from found to not found. So where did I get that? Well, it's 14 plus 10 versus 15 plus 10, so those two, versus 5 plus 20, which is 25, and 8 plus 20. So out of all of those, the 24 is the cheapest to get to v min. And it's probably not surprising, but sometimes the shortest edge is on the shortest path. So for example, we could have both to get to v star and x is 20, and in this case it makes sense, we're going to take that shortest edge here. And again, something to remember is we never have to worry about the case that later on we're going to have some big negative number over here. That's something we'll solve with different algorithms. So for example, when we get to the Bellman-Ford algorithm, it'll handle this problem for us. But we just never have to worry about that for Dijkstra because we work under the assumption that all edge weights are positive, or non-negative. All right, so what's our correctness summary here? Given our assumption that we do not have negative edges and our inductive hypothesis that our path to v star is the shortest, our analysis of Dijkstra's greedy criterion and a bunch of those different paths have shown that this path here is the best available path and that we will never go back and find a shorter path.